Okay, welcome to lecture 2 and part 4. We are going on to more potential divider circuits, right? So last week we stopped at this portion. We talked about the potential divider circuit involving two or more fixed resistors in series. And then we say that basically to get this V out, right, we just need to control the ratio of R1 to R1 plus R2. Okay, R1 over the sum of the total resistance. Of course, if we have a variable resistor here, we are able to make use of this to adjust the amount of the proportion of the resistance here, and therefore adjust V out as well. So that was where we stopped. Right, so we're going to move on to something else today. Right, now instead of using a pair of resistors, we could use a resistance wire. So this resistance wire is basically a wire of uniform cross-sectional area and resistivity. Right, so if this arrow here refers to a slider. So this slider can move along this wire between point A to point B. Right, so by shifting this sliding contact, we can vary the output voltage of the external circuit. Right, so again, this is a connection to external circuit, and this is your usual EMF, your single EMF circuit with a current going through it. Right, so we'll see how we can do the calculation for this part. Right, so right now we have this cable here, and we have marked out some lengths here, and there's a point A to point B, and the point C is where the contact is. Right, so let's do the calculation now. Right, so when there's no current from external circuit to the potential divider circuit, current through wire AB is just I. So what we are saying here is that the current from the external circuit does not come back into here. Right, so whatever current that's coming out from the EMF source I, it's the same current that's going into the resistance wire AB here. Alright, so once you have that, we can say V in is equals to I times RAB. Okay, so this potential drop, this terminal voltage here, is equals to the current multiplied by resistance of AB. Okay, because resistance of AB can be obtained using the formula rho L over A. So the length is length of AB multiplied by resistivity of the wire's material divided by cross-sectional area A of the wire, and just multiply by my current to get V in. And similarly, to get VAC, okay, which is my V out here, I just do I times RAC. Okay, RAC, everything's the same as the top formula, just that now I'm using AC instead of length of AC instead of length of AB. Right, and once you put these two things together, we can take the ratio, V in over V out is just equals to RAB over RAC, because I can cancel the i's. Then if I equate on this side, I will get LAB multiplied by, wait, is there a typo here? I think it's a typo here. So let me change the typo for you. Right, this is not supposed to be there, so this is supposed to be gone. It's just LAB over LAC. Let me double check quickly. Yeah, there should not be a cross-sectional area there, right? Okay, then let's continue. So if we rearrange this formula there, we can get this equation here. So I'm going to push my V out to the right hand side and shift the LAB with LAC back to the left hand side. So I get V out equals to LAC over LAB times V in. Basically, you can see that this V out here is equals to the proportion that this length has, okay, over the whole length. Okay, so right now you can see how you can adjust the position of the sliding contact to get a larger output voltage. Okay, the more you slide to the right hand side, that means you tap across a longer part of the wire, you get a larger V output. And then conversely, you slide this all the way to the left hand side, where you're tapping across a very short stretch of the wire, you will reduce your V output. Right? Okay, so later we'll try some examples, but right now let's move on to another type of potential divider circuit that involves a thermistor. So we are using a negative temperature coefficient thermistor here. So we can set up this PD circuit as well. Okay, what's a negative temperature coefficient thermistor, NTC thermistor? Okay, it means that when the temperature increases, when the temperature of the thermistor increases, the resistance of the thermistor will decrease. So the warmer it gets, the lower the resistance. Okay, for the theory about this, you have probably seen a bit in under COE. But I think, yep, you can just revise from there. You don't really have to know how it works. You just need to understand that your temperature, as the temperature increases, your resistance will drop. Okay, so you can set up this circuit. So right now I have this. This is similar to the first type of PDC we have, right? And you have RT, which is your NTC thermistor here, and a fixed resistor R1 here, right? So if my output voltage is tapped across R1, so you can see that if I want to find V, I take R1 over R1 plus RT times V in. Okay, so as temperature increases, RT decreases, and then V out increases. Right, so you can think of what the possible uses for this type of circuit. So one thing that comes straight to mind is that, okay, if I have aircon control, a climate control aircon, when the temperature of the surrounding increases, this resistance will decrease and then V out increases, right? This will mean that the aircon will pump out, will have more power sent to it, and then you can basically cool down the room better, right? And what happens if you switch R1 and RT? Okay, so this one, okay, then if you switch it around, you think about it, then it will change as temperature increases, RT decreases, then V out will decrease, right? So you can think of what applications you want to use for this. I leave it for you to discuss with your tutor. All right. Next, we have a PDC that involves a light dependent resistor. Okay, a light dependent resistor or LDR. The resistance decreases with increasing light intensity. Again, theory, you have talked briefly about it under COE. Basically, with light incident, it frees up more charge carriers within the LDR. Right, so you can again set up this potential divider circuit where V out depends on light intensity as well. So same setup as previous one. Your RL is on top. Okay, this is your LDR. So when light is incident on it, the resistance will decrease, and therefore V out here will increase. Okay, so again by this formula. So if what possible use we can have for this? Can't think of anything right now actually. Yeah, if it's the other way around, it would be easier because when you have light intensity. Yeah, if it's that way around, then you will have it as a switch that triggers at night lah. So or this one could be something like, for example, if you are setting up a security system when you have light incident on your LDR, basically it could mean that there's an intruder in the area who's shining a torchlight around, and you may want to do something to the circuit. All right. Okay. So again, R1, RL switch position. Again, you can discuss. Okay, let's look at example 7. Okay, I have a light dependent resistor that's connected in series with a 12 kilo ohm resistor and a 9 volt source as shown. Right, determine the potential at point P when the LDR is in the dark and has a resistance of 6 mega ohm, and in bright light where it has a resistance of 1 kilo ohm. Okay, let's see what we can do with this. Stop clicking. Alright. Alright, so let's do the first part. We know that VAB is always equal to 9 volts. Okay, if you tap VA to VB, we'll get 9 volts. In fact, the potential of A is at 9, and we set the potential of B to be 0. Because this is at Earth, therefore, because we know this drop is 9 volts, right? So VA must be at 9 volts. Right? Then we are supposed to find VPB now. Okay, because we need to find, in order to find potential at P, right? We need to work out either VAP or VPB. So I'll work out VPB instead, which is the potential across the LDR. Right? So at in the dark, the resistance of LDR is 6 mega ohms. So this is resistance of the LDR over resistance of LDR plus resistance of the fixed resistor 12,000 ohms. Okay, and then multiply by VAB, I'll get 8.98 volts. Right? So that means VPB, which is equals to VP, potential at P, minus potential at B, they'll give me 8.98. Right? So VP minus 0 because VB is 0, which means VP is 8.98 volts. Right? So we can do the very similar calculation for in bright light, where obviously the resistance will drop to a very, very low level. Alright. So right now, if you're trying to find VPB again, I'll be substituting 1 times 10 power 3 over 1 times 10 power 3 plus 12 times 10 power 3 and multiply by VAB. Then now realize, this potential difference is only 0.69 volts compared to the 8.98 previously. Okay, doing the same calculation, we can get VP to be 0.69 volts. Right? So I think it's quite straightforward here. You should just you can just use the normal potential divider equation. Right? Moving on, let's look at example 8 now. Okay, this thermistor here has a resistance of 4 kilo ohm when its temperature is 30 degrees Celsius at 8 kilo ohm, when the temperature is 10 degrees Celsius. So remember, the lower the temperature, the higher the resistance. So the temperature went from 30 to 10, resistance went up from 4 to 8 kilo ohms. Determine the change in the voltmeter's ideal voltmeter reading when the temperature drops from 30 degrees to 10 degrees Celsius. So just to note, if we never tell anything about the voltmeter, you can just assume it to be ideal. Okay, so this voltmeter has infinite resistance, so no current will go through here. All right, so let's look at this one now. Again, calculation is not too difficult. All right, let's just click pause. Okay, so let V be the reading across the 5 kilo ohm resistor. All right, so at 30 degrees Celsius, V is equals to 5,000 over 5,000 plus 4,000 from this one here, 4,000, and multiply by 9 volts, and my reading is 5.0 volts. Okay, then at 10 degrees Celsius, we do the same calculation, but instead of using 4 times 10 power 3, we use 8 times 10 power 3, and we get an answer of 3.5 volts. So the change in your voltmeter reading will be 1.5 volts in all. All right, quite straightforward, this one. Okay, this is the hard question for this section. Okay, I have a potential divider. It has a constant supply of 6 volts as shown in the diagrams. Which circuit will provide a potential difference between X and Y that can be varied between 0 and 3.0 volts? Okay, so if you look at the setup here, there's a slider here. This slider is basically adjusted along this stretch of R. So what's happening in real life here, probably this is a resistance wire here. Alright, so then you're just tapping different points of the wire. So to answer this question, right, we need to find a point, like for example, we look at Y and X here, right? We want a setup such that as I move this slider, I can get values. I can get Vyx to be between 0 volts to 3 volts. Alright. So we need to see where it is tapping. So I'll show you what I'm doing here. So first thing first, we'll lay out the potentials at various points in the circuit. If you look at the numbers now, alright, so you have 0 at the bottom, and then 3 in the middle, and 6 at the top. Alright, so it's the same for all of them. Okay, we'll look at option A first. Right, option A, if I were to tap this way, what I'm going to have is that I will have a potential divider that is, okay, let me just quickly draw it for you. Right, I can move this slider up and down this stretch, so I can take either none of this top resistor or 100% of this top resistor. So right now, your potential divider circuit actually exists like this. Let me just draw it for you. You have one resistor here, okay, and then you have the other resistor here, okay. So in this case, right, you can go down, you can set this bottom resistor, right, to be as large as the whole of the two resistors. Let's just say that each of them has a resistance of R. Okay, so you can set this to be as low as over here as R. Okay, when it's here, right, you will take half of the total resistance, because the total resistance here is 2R. Okay, or you can set all the way up to here. If it's all the way up to here, right, then your resistance will be 2R. Alright, that means what happens is that this range is actually from 3 volts to 6 volts. Right, you can use the potential divider concept to go and solve this. Okay, so if you just imagine lower to this point here, right, this point here, let me just go back to the highlighter. This point here, right, then my potential drop across my Yx, right, will be R over R plus R times your 6 volts. So it'll be between 3 volts to minimum will be 3 volts. Alright, so this is option A, and that's not the answer that we're looking for. Okay, we're going to look at option C now. Option C is a bit more complex, but let's try to stay together with this one. Alright, so option C, right, I'm always tapping across the top and bottom. So it seems that I will get a constant, it does not appear to vary, right? But what will happen now is that this, okay, so if you look at the path, what will happen is that no matter what I'm doing, right, I'm always tapping across the whole stretch from 6 to 0. Okay, your current right now will travel down, follow my cursor, travel down through this green stretch of resistor, then jump across to here, across this wire here, then down through the purple resistor. Okay, the best case scenario is that if you shift this all the way down to here, and then you just travel down this way, and then basically, if it's down to here, right, then this wire is not doing anything, you just go down. But right now, what you're doing is that you are not actually setting up a potential divider circuit. You are still tapping across the entire, your y-axis is still connected across the entire resistors here. So right now, your resistance will either be as small as R. Okay, if you connect this all the way to the top here, it'll be as small as R because you're just using the purple color resistor. You'll be using the sliding cable to bypass. But if you slide it all the way down here, your resistance will be 2R. Okay, but again, no matter what your value of resistance is between this stretch, right, you are still tapping across the 6 volt and the 0 volt point. So your resistance, your PD across XY here will always be equals to 6 volts. There's no change in the value. Okay, let's look at the option D, which is also wrong. Okay, option D, right? We are now tapping at this point here. So if we can see now, this is the potential that we are always, this is the resistor that we're always tapping across. So to find VXY, right, it's always R, because this is R, over R plus whatever that's tapping across the top. Okay, so this slider here, what it does is that it is allowing you to bypass the non-colored part of the resistor. So you can tap down to here. If I slide the slider all the way up to the top, it will use the entire resistance. So if it does that, then this portion here, it can either be between 0% coverage or 100% coverage. Okay, so my total resistance will depend. If my slider is the bottom here, the total resistance this whole stretch will just be equals to this R. But if I slide all the way to the top over here, I'm getting the full stretch of R here, and this will be X R plus 1 times R. Okay, so if that's the case, right, my value here, because my X ranges from 0 to 1, this value R over R plus XR will range between 0.5 to 1. Right? Minimum, it will be, if X is 0, this whole thing will be equals to 1. If X is equals to 1, this whole ratio will be equals to half. Okay, so the range of the PD across XY, right, will be 3 volts to 6 volts. Okay, and therefore option B is our answer, but let's just see why option B is the answer. All right, option B, my top end Y is always tapped to the 6 volt potential. X is sliding along the first resistor. All right, and again, now the rest of the resistor is over here. Let me just highlight it for you again. So I have one resistor here. Let me box it up. And then the second resistor in series is over here. Let me just shade it for you. Right? So your ratio is the maximum size this green resistor can be is R. The smallest it can be is 0. The total resistance here is always equals to 2R. Alright, because it's always equals to 2R, so my range of this is from 3. This N will always be between 3 to 6 volts. Alright, so then therefore your range, because the top is always 6 volts, right? So this is between 3 to 6, right? So the range will be between 0 to 3 volts. Okay, so the answer here is B, right? So this is a toughest question over here. And with that, I think we are done with this part. You can go on to try the rest of the sections here before moving on to the next part of the lecture. Thank you.